Now after you run this, it will produce the particle filter mean.txt file. Let's load this. And now what you see here is in green all the particles for step number 0, and in blue the current mean position and mean heading. And as we cycle through the trajectory, we see how in every step the mean is computed, which gives us one single position for every filter step, similarly to the Kalman filter. Now for example here, we see a typical effect. Now in the curve, some of the particles spread out and move the mean position a little bit to the right. Now in the next step, those particles have died out, and in consequence, our position jumps a little bit to the left. So this is what you see here. Also down here, the trajectory is not very smooth, but this depends on the number of particles. So I ran the same algorithm with 200 particles instead of 50. Let's load this. And as you see, the trajectory looks much smoother now, although the larger number of particles does not prevent small steps in the trajectory, as you can see here. Now let's have a look at this. Here we can see clearly how some of the particles spread out and take a smaller curve radius, and then eventually they die out. Now if we compare this to the reference, we see that we obtain globally a very good solution. Now let's have a look at the start and the end of our trajectory once more. So in the beginning, our robot does not move for a few steps. So these are all the particles, and they are spread according to the sigma in our initialization. So now if we move for 1, 2, 3, 4, 5 steps, we see that the number of unique particles decreases rapidly. So that shortly before we start to move, we only seem to have a few particles. Well, we still have 200 particles here, but we only have a few unique particles. Now as we move, the situation tends to get better. But in the end, when the robot comes to a halt, the number of particles again decreases. Now where does this come from? So assume we have those particles, now the robot moves, we sample from those distributions, get those particles, then we give them some weights, and then we do the resampling, where we typically may lose particles with a very low weight, whereas we tend to draw several identical particles for particles with a high weight. So we have this situation, so we reduce the number of unique particles by 1. However, if we now move again, this doesn't matter so much, because we move here, we sample from the distribution. We move the second point also here and sample from the distribution and get another point. And so after picking the particles from those distributions, we again have 4 unique points. Unfortunately, if we don't move, then this step, where identical particles are spread out again due to the sampling from this distribution, does not happen. So if we don't move, all that happens is we occasionally drop 1 particle, so we have 2 here, but then if we still don't move, we might also drop this particle, and so as you see, the number of unique particles is reduced, until eventually, after some time, we end up with 1 single particle. And so, what you see here, for the extreme case of a robot that does not move at all, holds in fact in general, which means that if I resample too often, I may lose diversity, as we just have seen for the case of a robot that doesn't move at all. On the other hand, resampling too seldom wastes particles in low probability regions. And in fact, the reason for our resampling was that we wanted to drop particles which are in regions that have a very low probability. And so as you see, there's a trade-off here, and the solution we have so far does a resampling in every filter step, which may be too often. And we noticed that we reduced the number of unique particles while the robot stood still. And one of the simplest measures against this is just to do no resampling while the robot is static. So if our control tells us there's 0 movement of the left and right track, we simply do not do a resampling, and usually it's also a good idea to discard the measurements. So we can also integrate multiple measurements into our weights. So remember, the way we treated our weights was we compute the weights, we do the resampling, and we just discard all the weights, and then in the next filter step we compute the weights for the new particles. So we don't keep them. However, we could also keep them, and so if we did a resampling, we reinitialize them to be 1 if the resampling took place, whereas we multiply them by the probability of our current measurement if no resampling took place. So when should we resample? And there's a standard approach here to use the variance of the weights to determine if resampling is necessary. But we won't have a closer look at this. Now let's have a look at this solution. Now implementing this solution is very easy because all there is to do is, in the main function, we check if our control is not equal to 0, and if so, we do the prediction and the correction step, and if not, we just leave that out and directly jump to the printout of our particles and the determination of our mean. Now in the code you see here, I also did some other modifications, and I invite you to do those modifications to your own code. So this if control not equal to 0, 0, and also this modification. So earlier, I motivated that one of the main advantages of the particle filter is that it is able to do global localization. But up to now, we initialized our particles to be close to our start state, which we have determined somehow by hand. Now let's do something different. Now let's initialize all the particles just using a uniform distribution between 0 and 2000 millimeters for x, y, and the heading between minus pi and plus pi. So indeed, our particles spread out over the entire arena with arbitrary orientations. And now the hope is that even though we do not know our initial position at all, we will still be able, after some startup maybe, to determine our global trajectory. And here's the third modification you may play with. So far we have computed the mean, but we can also compute the second moments. So we take the mean, we take every particle, subtract the mean in x and y, which is now called center x, center y, and accumulate the sums xx, xy, and yy, and divide that by the number of particles minus 1. And this is the covariance matrix. And for the covariance matrix, we compute the eigenvalues and eigenvectors and use those to compute the orientation of our error ellipse as well as both half-axes. And here we compute the variance of the heading and return that as well. And below in the main program, here in this section, we output the error ellipse and the heading variance. And this uses the very same records, the E records, which we introduced in the last unit about the Kalman filter. Now one more remark. If you run this, you have to select a certain number of particles. And so if you use 50 as we did previously, then they are spread out in our arena so much that the chance that there is a particle close enough to our correct but unknown initial position is so low that probably the filter will not be able to recover the trajectory. So you need a higher number of particles, and I've chosen 500 here. So now let's have a look. So these are our particles when we start, and they are uniformly distributed. And now from all those particles, the mean is somewhere in the middle of the arena. Our error ellipse looks like that, so it is a circle. And our heading just points somewhere with a high variance. Now when we start to move, nothing happens. This is because as long as our left and right control is 0, our particle filter does not do anything. So let's move on. And here, from step 12 to 13, we have our first move, and the particle filter starts to predict and correct. And so after this first move, we see that only a few unique particle locations remain, and obviously there are so many particles around here that the mean is already very close to our true position. Let's do one more step. Now most particles are concentrated here, and now we start to move. And again we see very nicely how the particles spread out in the curve, which is also reflected in the larger error ellipse and the larger variance in heading. And as we go straight, the error ellipse is smaller and also the variance in heading is much smaller. Now if we also load the landmarks and the reference, we see that indeed, although the particle filter quickly determines the correct position approximately, it still needs a while to converge to the correct position. So probably this here in the beginning show us that our variances of the error that we assumed are too small and need to be set larger in order to have a faster convergence to the true trajectory. Nevertheless, I find it very amazing that without any knowledge of our initial state, the particle filter manages to get very close to the true state very quickly. There's one more thing I want to mention, and this is particle deprivation. Now remember, we have our particles, and remember our case with the trajectory where the true movement is like that, but some of the particles actually moved like that, and eventually they died out. However, what might also happen is that by an unlucky series of random numbers, we might pick many particles here, and then from the remaining ones, we unfortunately delete all particles that follow the true track, which we don't know. And so we end up with a lot of particles here, and no particle at all on the true track. Now, those particles would fit much better to the measurements of our laser scanner, but unfortunately, all particles that remain are here. And the weights that I determine, they're not absolute, but just relative. So I go on weighting those particles, and even though in absolute terms the weights are pretty small, much smaller than the weights I would obtain here, I have no chance of ever selecting again one of those particles because they all died out. And so since this is all a random process, it might always happen that there's particles on the true trajectory, and just by the pick of the random numbers, they suddenly all die out, although the probability for this to happen is very small. And so particle deprivation means that an unlucky series of random numbers may delete all particles near the true state. And this typically occurs, of course, if the number of particles is too small. And one popular measure, which is not really a solution to that problem, is to add some random particles after resampling. So it is not really a solution because still the problem might occur, but this at least reduces the probability of a wipeout. So in this case here, we would add some random particles, and due to the fact that one of those random particles is close to the real state, its weight would be much larger than the other weights, and so in resampling, this would quickly gather many more particles, and eventually this solution would die out. Now the downside of this is that by adding random particles, I modify the distribution, and so I obtain an incorrect posterior. Now congratulations! In this unit, you implemented a fully functional particle filter which is able to determine the position and heading of our small robot even if we don't have any initial information about the robot's pose. And I think this is a pretty amazing result. So we learned to know the particle filter, which we used for localization, and which is also known as Monte Carlo localization. And we've seen there are some caveats. For example, we need density estimation. That is, after we predict and correct all our particles, we still have to extract the state of our robot because we need that, for example, to do a planning of our trajectory. And we have used a very simple density estimation, which consisted of computing the mean and covariance matrix of all the particles. And we also have seen the problem of particle deprivation, which we didn't treat in detail. However, we also have seen that the particle filter is very easy to implement. So if you compare that to the Kalman filter, in the case of the Kalman filter, we had to compute several different derivative matrices, and the computation of the Kalman gain and the new state and new covariance required several matrix operations. Now, as you remember here in the particle filter, we did not need any matrix operation, and in fact, in our implementation, we did not include numerical Python. And so since it is so easy to implement, the particle filter is very popular, especially in robotics. So again, congratulations, and I hope you join me in the next unit.